All right, let's get started for today. I've got a new project to get to work on, a new branch on an existing project. As my usual reminder goes, if you're into the binary deep dive stuff I've been doing with PE and cough up until now, or the bin dash stuff, or my YouTube projects, or anything else I've got going on, keep in mind that all of that is funded by people like you who think that what I'm doing is cool and decide that you want to keep it going by going to mrforth.com/membership and checking out the supporter and membership perks. It's much appreciated to all the people who do make that decision. And with that, let's get into the project. I want to shift gears now here on stream. Off stream, I'm working on bin dash. But on stream, I'd like to switch over to making another dumper. So we made the PE dumper to get this whole thing started. And so now we can inspect PE cough files thanks to the work that started here. And I'd like to begin doing the same kind of work again with an ELF file dumper. So ELF is the binary format used on Linux. PE and cough are used on Windows. ELF is used on Linux. So we want to go in and start filling in this section right here, ELF dumper. So ELF, well, let's do it this way. Boom. Let's start by setting up where the new code is going to go. Binary project. All right, all of these are going to go into a new PE folder. Yes, let me go and reorganize things actually. Please live here. Now I want to track down Mr. Forth PE.dump. These are now in the PE folder. Anywhere where it says binary slash Mr. Forth PE, I need to change it to say binary slash PE slash Mr. Forth PE. Nice. Okay. So while I'm not working on the PE dumper or bin dash, let's drop those. And let's get started on a new one. Elf slash Mr. Forth elf.dump.c elf.dump source binary elf yes. And now let's see. I probably want a Mr. Forth elf.h. That's gonna run parallel to the pe.h. Executable and linkable format. Here we go. Elf. use the Wikipedia documentation. I thought this would link to the documentation. I don't want to use this either. But maybe this is a good one. I know there are better docs than these, so that's disappointing. My first time trying to use this, no good. I know there's a better one. Here we go. This is the one I think I'm looking for. Is this the one I'm looking for? I think this is the right one. Okay, got a link in chat that I'll check out. Yeah, this isn't the one I'm looking for. No. No. I think this is the one I like. Object files participate in program linking, building a program, and program execution, running a program. For convenience and efficiency, the object file format provides parallel views of a file's contents reflecting the differing needs of these activities. Figure 4.1 shows an object files organization. Object file, elf header, program header table, optional, section 1, section N, section header table required. Elf header, program header table required, segment 1, segment 2, segment 3, ... Presumably all the way until segment N. You didn't say it went all the way to segment N, but I assume that's what it does. All of this N and that N wouldn't be the same. That's not what I'm saying. Section optional header, or section header optional. Yep. At the beginning, hold a roadmap describing the file's organization. Sections hold the bulk of the object file information. Linking view, instructions, data, symbol table, relocation, information, and so on. Descriptions of special sections appear later in the chapter. Chapter 5 discusses segments and the program execution view of the file. A program header table tells the system how to create a process image. Okay, blah 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 blah. Data representation is described here. The object file format supports various processors with 8-bit bytes and either 32-bit or 64-bit architectures. Nevertheless, it is intended to be extensible to larger or smaller architectures. Object files therefore represent some control data with a machine-independent format, making it possible to identify object files and interpret their content in a common way. Remaining data in an object file uses the encoding of the target processor regardless of the machine on which the file was created. Okay. Well, we found the right one. Here they're explaining that add or off, half word, and S word all mean for half is 2, unsigned char is 1, but word, sword, off, and adder are all 4s. But here, adder and off are 8s. Sword and 6 word are 8s, but sword and word are still 4s. Half is still 2. Got it. Okay. So adder and off are the only ones that actually base their size on the number of bits they put here when they're specifying it. Got it. So what we have to do is make a 32-bit and 64-bit version of each header because that's how all of ELF is organized. We're going to put this over here, and we're just going to get to work on the doing of the writing out the file format. Starts like this. We don't want all their weird types. Half means U16. Cool. All right, let's keep looking through the docs. What else we got? So there's headers. It's got some underneath this we get this member identifies the object file type. E-type. Okay, let's grab these. Must have messed those ones up. All right, what's next? Yeah, Elf is a little. The Linux stuff covers like everything that's ever existed. It's a lot. Yeah, we're pretty much done with PE, or at least we're done with what we can do by dumping and visualizing with bin dash right now. There's still a lot to do on it, but I think it's time for us on stream to make progress on the other half, on the Elf side, the Linux side. So version's always a 1. Virtual address to which the system first transfers control, thus starting the process if the file has no associated entry point. This member holds 0. This member holds the program header table's file offset in bytes. This member holds the program header table's file offset. Okay, file offsets to the program header table, section header table, processor specific flags for the file. Flags and make names take the form EF machine flag. Holds elf headers size in bytes. This member holds the size in bytes of one entry in the file's program header table. All entries are the same size. Here's a question. It must be in the eident that we haven't actually parsed yet. Okay. So now we need to look at the identification stuff. Okay. Let's grab these. go. Okay. Trying to decide if I want the names from the docs or descriptive names that help. In most of these, I've just kept the original name. It should help with pairing up what you're seeing in the interfaces to the documentation. I think I'll stick with that. Leave it up to a further documentation self-expository system within the interface to fix that someday. Okay, let's see here. OS or ABI specific ELF extensions used by this file. Some fields in other ELF structures have flags values that have operating system and or ABI specific meanings. The integration of those fields is determined by the value of this byte. Files do not use any extensions. Just recommend this byte be set to 0. Alright, so we'll just call this extensions then, OS ABI. There we go. That's how I got it right. Let's get the table lined up. All right. Hey, Batman, welcome. I'm going to be a little quiet today because I'm moving information from documentation into headers for the new format. The ELF dumper. Okay, that's everything to do with this page. ELF header. Let's go to the next. Sections. An object file's section header table lets one locate all the file sections. The section header table is an array of ELF32 shooter or ELF64 shooter structures as described below. A section header table index is a subscript into this array. The ELF header's eShof member gives the byte offset from the beginning of the file to the section header table. eShnum normally tells how many entries the section header table contains. Int size gives the size in bytes of each entry. If the number of sections is greater than or equal to lower reserve on def and the actual number of section header table entries is contained in the sh size field of the section header at index 0, otherwise the sh size member of the initial entry contains 0. Some section header table indexes are reserved in contexts where index size is restricted. For example, the shnix member of a symbol table entry and the ishnum and ishint members of the elf header. In such context, the reserved values do not represent actual sections in the object file. Also, in such context, an escape value indicates that the actual section index is to be found elsewhere in a larger field. Okay. Fair enough. Special section indexes. Undefined, low reserve, low proc, high proc, low OS, high OS. Abs, common, X index, high reserve. Okay. Here's the part where we want to start. This member specifies the name of the section. Right. We gotta do... You guys are out. Its value is an index into the section header string table section. Okay. This member categorizes the section's contents and semantics. Okay. Okay, so that goes to types. Shit goes away. And then we do... Let's see here. There we go. Mighty Loop, yeah, I've got Spall down there. Anytime I want to, I can go, I can go over to my variables here. And if I remember correctly, there's like, can't remember exactly how to do this. It's like profile. Yeah, I can turn on manual profiling like this. And then we'll start capturing Spall dumps and we can drop it into Spall. It's all part of my Codebase's features. Okay, question from Kata Imoi. Do you see any benefit of writing C code in CP files and using a C++ compiler? Not these days. I used to play with that, but now I'm just happy to write in C. I prefer it. The one thing that sucks about C is that most of the C compiler errors are a little goofy. Like if you use a function name that hasn't been declared, but you call it and you misspell it, or you got parameters wrong. C++ compilers give you better errors because C compilers just assume that that function is linkable, and you get a linker error when the linker can't link it. Whereas in C++, you get a compiler error with a little bit more niceness, but I would still want all my code to compile in a C compiler. I wouldn't want to be using any C++ features. The price is a bit steep. I can't remember how expensive Spall is. Let me take a look. Ooh, it's 75 bucks. I must have got it on sale. I think I got it for 50% off or something. I thought it was 50. And this is a 25% sale too. I can see why you would say that. Wait, the flags are 64-bit? I guess this is 64 bits here, so it might be just like a padding choice to make the flags bigger. Let me double check that though. Yeah, they use an X word. That's 64 bits. Okay. But I like that. Would I rather have it look like this? Yeah, that's probably better. Okay, so those are section types. Here's our section flags. God, I don't really understand your question. I would allocate. Um, I mean, I wouldn't write any the code that you wrote, but it really depends on what a unit is. There's not an abstractable question. The question is, do I allocate my units in blocks or in independent allocations? And it's not like that's not in the abstract. Unit is uncontexted data type, so I can't answer your question. You gotta fill in the gaps of like how does the unit relate? What is it? How does it relate to the other pieces? What are the lifetimes of the pieces it relates to? How does it relate to the code? What is it? All of that matters. But there's nothing. I would never be against using a block or independent allocations. I wouldn't use malloc though. Malloc is standard library. Heap. I wouldn't. I would probably never do that unless I was writing code for a very simple example or something. Okay, there's not going to be a type def on this because the section flags change size, but feel free to use C, but the question you're asking, should you free things independently of each other or allocate them in blocks and leave them sitting around when they're done, isn't a question I can answer without more detail because it's not all cases are the same. And it's not even a matter of like sometimes it's better this way and sometimes it's better that way. Some things just don't work one way or the other, right? Like you're asking as if I know what you mean by unit and I know what's happening in your program. There are cases where it makes perfect sense to allocate and deallocate things independently of each other with completely free lifetime constraints between them. So there, and then by completely free, what I mean is no constraints. It's free of constraint. You can have their lifetimes vary with respect to each other in any way you want. And a lot of times that's not true. And a lot of times, even if there are very few constraints on their lifetime relationship, you can live with one or two soft constraints. And so you're asking as if there's two options when there are actually like hundreds of ways to allocate memory and to organize that. And the answer is if you want to be learning C and you're new to it, then you should just do something that's working for you and learn how that works. Learn how to make that work. And then the next time you encounter a similar problem, do it different. Learn how all the different options work. Learn how to play with your tools. But if you're asking me which way you should do it without context, then I think you're missing the point. That the bigger point is there are lots of contexts and lots of tools. And your job as a programmer is to learn how to match up the right context to the right tool, not to learn which tool is the right tool or which context is your favorite. Your job is to learn the mappings between what you know how to do and what problems are worth solving. Malloc isn't bad practice. It's just I tend to avoid it for anything besides simple examples, because it ties in the C standard library, and I like to move in the direction of having as little time with the C standard library as possible. Um, Just because it's kind of like it's kind of an old design. Like for me, it feels better to just know where all the code is that I'm relying on, as much as possible. And malloc solves a problem that I very rarely want solved. Usually something simpler like an arena allocator or a pool gets the job done, and I can script up one of those in C in a day, in a morning, before I, it's just like it's not a big deal. So it just makes more sense to not rely on malloc. Personally, except unless I'm whipping up a quick example in a vacuum that I want to be done within an hour, and I have C, then I'll rely on the standard library to make it easy. That's the exception. Interesting. I don't remember actually working with compressed headers before, but let's get it. Part of the problem here will be finding example programs that actually, like example files that actually test out anything that I write for these kinds of things. If I wanted to give you the best advice I can give you is don't worry about what is bad practice. Bad practice is a made up word used to control the thinking of people who are in the process of learning. So if you want my advice, set yourself free, figure out what's best, figure out how to think about what's best on your own. That's the only way. And you're free to ask questions about why is this better or worse in my opinion, but if someone tells you don't do X because it's bad practice, your eyebrow should go up and you should be like, okay, buddy. Thanks, I appreciate the compliment. But yeah, if you just stick with it, all I've really done is spent years, decades. How old am I? I'm 28. Probably I'm close to 2 decades of programming experience now. I didn't start in C, so I'm not counting 2 decades of C. That's more like 10 years, like 1 decade. But it's just time. Just keep putting in the time. Okay. Compression type, compression header. Make these go away. Cool. If a link editor encounters sections whose headers contain OS-specific values it does not recognize in the sh type or sh flags fields, the link editor should combine those sections as described below. If the section's sh flags bits include the attribute OS nonconforming, then the section requires special knowledge to be correctly processed, and the link editor should reject the object containing the section with an error. Unrecognized sections that do not have OS nonconforming attribute are combined in a two-phase process. As the link editor combines sections using this process, it must honor the alignment constraints of the input sections asserted by the add or align field, padding between sections with 0 bytes if necessary, and producing a combination with the maximum alignment constraints of its component input sections. In the first phase, input sections that match in name, type, and attribute flags should be concatenated into a single section. The concatenation order should satisfy the requirements of any known input section attributes. Merge link order. When not otherwise constrained, sections should be omitted in input order. In the second phase, sections should be assigned to segments or other units based on their attribute flags. Sections of each particular unrecognized type should be assigned the same unit unless prevented by incompatible flags, and within a unit, sections of the same unrecognized type should be placed together if possible. Non-OS specific processing should be applied to unrecognized section types. Output section header table, if present, should contain entries for unknown sections, and the unrecognized section attribute flags should be removed. Okay. Section groups. Some sections occur in interrelated groups. For example, an out-of-line definition of an inline function might require, in addition to the section containing its executable instructions, a read-only data section containing literals referenced, or one or more debugging information sections, and other informational sections. Furthermore, there may be internal references among these sections that would not make sense if one of the sections were removed or replaced by a duplicate from another object. Therefore, such groups must be included or omitted from the linked object as a unit. A section cannot be a member of more than one group. A section of the type SHT group defines such a grouping of sections. The name of a symbol from one of the containing objects. Symbol tables provides a signature for the section group. The section header of the SHT group section specifies the identifying symbol entry. As described above, the SH link member contains the section header index of the symbol table section, contains the entry So nothing. Section group flags. The section data of SHT group section is an array of ELF 32 word entries. The first entry is a flag word. The remaining entries are a sequence of section header indices. Okay, so that does go there. Section group flags. Nice. Yeah, you're doing cool stuff. If you keep it up, you'll go far. It's really great. It's a really great amount of sort of interacting systems that I can already see in the sample you just sent. They make this sound so goddamn complicated. Okay. Don't care about any of that. Alright, so that's sections. String table. String table sections hold null terminated character sequences, commonly called strings. The object file uses these strings to represent symbol and section names. One references a string as an index into the string table section. The first byte, which is index 0, is defined to hold a null character. Likewise, a string table's last byte is defined to hold a null character. Ensuring null termination for all strings. A string whose index is 0 specifies either no name or a null name, depending on the context. An empty string table section is permitted. Its section headers sh size member would contain 0. Non-zero indexes are invalid for an empty string table. A section header's sh name member holds an index into the section header string table int section, as designated by the sh string index member of the elf header. The following figures show a string table with 25 bytes and strings associated with various indexes. Okay, it's easy enough. An object file symbol table holds information needed to locate and relocate a program's symbolic definitions and references. A symbol table index is a subscript into this array. Index 0 both designates the first entry in the table and serves as the undefined symbol index. The contents of the initial entry are specified later in this section. Here we go. Symbol. Okay, so size. This member specifies the symbol's type and binding attributes. A list of the values and meanings appears below. Following code shows how to manipulate the values for both 32 and 64-bit objects. So let's see here. This applies to the info field, which is 1 byte in either case, and is exactly the same, so no need for the distinction. So what we're really saying here is elf bind from info. So this will be symbol bind from info. We'll call this inf to make it clear what the input is there. Symbol, what is this? Type from info. Inf is inf and the low 4 bits. Okay, so high 4 bits, low 4 bits. Elf symbol info from bind type and tip bin 4 together with type mask, and there we go. Alrighty, I am going to stop right here for a moment to take a little break. I think we made some good progress. Been at it for a little over an hour. That's good. All right. So we got all of this. Okay. So here we go. We need to write down these symbol bindings. Let's see. USD approved asks a really great question. Unless it's USDA approved, either way, has all this work on executable formats given you an idea on how you design your own format? Okay. That gives me a chance to talk about how I see all these things fitting together from a really interesting angle. So, I am not really thinking about designing a binary format deeply yet, although I do have some inklings of ideas of what I would do. I think in order to design a new format better, we would also need to study the processes related more than we have. So the format is useful, and getting good at it means being able to like inspect it better and to generate copies, like instances of it better. But to design a replacement would mean we would need to study all of the processes that this format is involved in. And our parsers and generators are only about half of those processes. And uh, the other half of the processes we need to know about are linking and loading, right? Linking is the process of turning object files into executables, and loading is the process of turning executable files into running, executing programs that are like actually happening. And that second piece is especially, there's a lot there that is interesting. A blending of those possibilities of constructing programs, of running programs. If we were to go into those and think about what kinds of things we want from software that we don't get, like, for instance, if we were working on plugin systems and we were thinking, hey, is it really necessary for binding of plugin inputs to the main program and the feedback channels between these two things, the communication? Have we structured this in a way that maximizes the potential of the computer and the potential for interfaces that compose software like this? Have all this is all this working the way we want, or can we imagine more stuff that works better in this space? And I think the second case is true. I think if we spend time there, we would imagine more stuff. But I think that it's a little hard to fully get your head around those things until you've made better baby steps up to seeing what all the details look like, right? At the high level I can pitch that. What the hell am I talking about? Well, we would need to go and study all the low level details of those processes, and then we could start talking about what is possible to build, and then the set of all of our imaginary things we'd like to build, and the set of all the things that are possible to build would both be in view, and the Venn diagram where those two things overlap would be what I would design, right? But it's hard to talk about what that would be because it's an unknown. There's a research problem between here and there, which is getting good at the current practical details about how these things are currently working, because I don't want to throw away important features that have been thought through already just because I have a cool idea. What do you mean by a fit check? What do you want to know about it? It's I agree it's my favorite shirt. And it fits me well, but I don't know lingo. So I don't know what you're actually asking for. But I appreciate the positive feedback on my favorite shirt. That's for sure. Okay, we've got a symbol binding enum. Symbol types, okay. Symbol visibility. What do you got? STUV, go away. Record, X, parenthesis, go to the end, back up, mark, backward, forward, delete, comma, space, end, parenthesis, end. Boom. That's how we macro. There's our symbol visibility. Symbol's value refers to a specific location within a section. Its section index member holds an index in the section header table. As the section moves during relocation, the symbol's value changes as well, and references to the symbol continue to point to the same location in the program. Some special section indexes values give other semantics. The symbol has an absolute value that will not change because of relocation. The symbol labels a common block. Okay, so are these section indexes things we already knew about? Let's go back to this one. Maybe this listed some special section index types. that I skipped. Yeah, we do want these. Okay, so let's go back and take those. I skipped them before. Elf section indexes. Boom. All right, on to symbol table stuff. So we got bindings, we got symbol types, we got symbol visibilities. We got the null version. Okay, this is information about behavior. Okay. Relocation is the process of connecting symbolic references with symbolic definitions. For example, when a program calls a function, the associated call instruction must transfer control to the proper destination address at execution. Relocatable files must have relocation entries, which are necessary because they contain information that describes how to modify their section contents. All right, to go back to a previous question, ideas on a new format. Here's something I would change. Relocations are perpetually more complicated than they need to be. Across all the work I've ever done on binaries, there's always tons and tons of detail put into the relocation system, and what it is actually achieving, what it needs to get done, is so simple that it could have been done once in such a way that you would write the code in about 15 to 20 minutes, and it would work for every file type. It wouldn't matter what architecture you're talking about. It wouldn't matter what operating system you're talking about. It's just so simple. And the fact that it's always complicated is mind-boggling. But I think a part of the reason is that people expected this to be a hard problem for a long time, and it never got that way. It never became as bad as they thought it would be. Because it's written in a way that makes it feel very like low-level, crunchy, nasty. It's not. It's pretty simple. It could be, at least. So, relocation entries. Okay. What does the A stand for? Okay, so we need 64, or this is 30, relocation, add That's what the A stands for. It stands for addendum, so I will shorten that to add. S32 addend. Elf relocation 64. U64 offset. U64 info. S64 addend. Relocation add. Okay, we'll come back to this if we're ever looking at relocations. We're gonna go ahead and let's open this up and add this to a new group. Let's color it purple. Call it the elf group. Have this living in here next to our other groups. This color theme right here, Buka, is that the one you're asking about? This is the 4-coder color theme. If I go to theme lister, this is the theme called 4-coder. You can, to give you a little more information, you can go over to 4-coder and go to, actually, you know what? I don't have a link here to the, let's go to the 4-coder community 4cc. If you go into the, themes folder, look at theme-4coder. There you can get all the color codes that go with it, the background and the somewhere in here. Text cycle back. Where is the text default? It's a little farther down than I thought. Text default, comments, keywords, all that. It's all right there. Okay. Doesn't really prove anything. I don't need to run bin dash right now. But it builds. That's the important point. If elfdump builds, then all of my code is well written. It's compiling. It doesn't do much yet. It's just a bunch of types, but it compiles. And that's good. Good place to start. Alright, so we got to the end of chapter 4 with relocations. Now we're going on to chapter 5 with program loading. So this is the part that deals with the elf header, the sections, and everything related to the linking process. This is going to tell us more about the program headers, which we haven't touched yet, the concept of segments, and the runtime linking / loading processes. Program headers, okay. We're going to call these segment 32 of segment instead of program header. Yep. Okay. Word offset adder x word. Okay, the types look like this. Elf segment type. I think that might be a good place to stop. Elf segment type xlist. So it takes a U32 to stand for an elf segment type. Segment type. Okay. I'm not sure I understand your question. So someone is asking, Bretolette is asking, are you converting C to something else? I'm not sure what you mean, but no, that's not happening. I'm not really sure. I'm not really sure what gave you that idea. So curious to hear an explanation of what you're thinking and what you're seeing, so that I can help you understand a little better what we're doing. A program to be loaded by the system must have at least one loadable segment, although this is not required by the file format. When the system creates loadable segment memory images, it gives access permissions as specified in the P flags member. So these are segment flags. Okay. Segment flags. Yeah, I'm I'm just writing C code. I'm not changing the C code because I want to stop using C code. It's just this is my C code and I am working on it. I don't really care to work with Zig or any other language. They're all to me they're all about as good as C. I don't I know to a lot of people big differences in like a different language is a big difference, but like if it compiles languages that compile are pretty much all the same to me. I feel kind of blind to whatever it is that people are so excited about in new languages. Except that I do understand like the learning experience on newer languages is usually better. C's weird, hard to learn in the sense that like it's no longer designed to make sense to the modern world and uh, no longer popular enough to have everyone helping everyone else out when it comes to understanding it. But for me, it works great. There we go. Nice catch. All right, so elf segment flags. Oh, that's not the flags. Flags. They reorder them between the 32-bit and 64-bit versions for packing reasons, but it's a little confusing. Anyway. An object file segment comprises one or more sections, though this fact is transparent to the program header. Whether the file segment holds one or many sections also is immaterial to program loading. Nonetheless, various data must be present for program execution, dynamic linking, and so on. The diagrams below illustrate segments, contents, in general terms. The order and membership of sections within a segment may vary. Moreover, processor-specific constraints may alter the examples below. See the processor supplement for details. Text segment. .data.dynamic.god.bss. Dynamic program header element points to the dynamic section. The GOT and PLT sections also hold information related to position independent code and dynamic linking. Note section. Sometimes a vendor or system builder needs to mark an object file with special information that other programs will check for conformance, compatibility, etc. Sections of the type should note and program header elements of the type putty note can be used for this purpose. Okay, notes. Okay, ignoring this. It's not the specification. I'm using the default theme -4 coder, although that might not have everything you're looking for in it. I think it does. Where did that come from? Go away. I think that's everything that I'm relying on. Yeah, I mean, this is the one I use right here. I don't see any reason why it should be different. Look at the history of this file. No, yeah, that's just the way it's always been. Shit, no bits. Yep, that's my theme. Enjoy, it's my favorite. I wish everyone loved the four-color theme. I think it's so cool. I'm glad you're into it. Do I want to grab this thread storage? What do they even call this? A program entry has the following members. This isn't a struct. This is the program header. TLS. Yeah, so if I find a program header with a type TLS, this tells me more about it, but that's not actually telling me more about the format. That's telling me more about the dynamic loading process. Okay. I think that's everything. Went through program header, program interpretation, dynamic linker, dynamic section, shared object dependencies, institution, global offset table, procedure, linkage table, hash table. I'm not sure if I've been through any of this stuff before. This doesn't seem like the part that I care about. Shared object dependencies. Yeah, I think we're good. Keeping this around. All right, so that gives us all the types that we need to start getting into Elf. Let's finish up with going over to Elf dump and just putting in the template stuff that we need. Let's actually start with PE dump header. Okay. Let's grab some of this. Okay. Now things get different. We're going to go straight into checking the first 4 bytes for magic. So there's our magic check, and then we can do ident check. But let's see, we also want to grab each of these things, right? We want to be able to say like elf class identification index class encoding Now the next part is we need to get a header. Now this part starts to get annoying because at this point we need to use the class to determine if we're doing 32-bit or 64-bit layouts every step of the way. We could later on simplify by translating everything up to little endian 64-bit. But for now we won't. We'll have to do it this way. Okay. Um, so we grab the elf header, and then we're going to grab the list of sections and the list of segments, and we want to be able to dump all of that. So let's do translate header up elf header 64 header 0. If header 32 raw does not equal 0, then elf header 64 from header 32 header 32 raw, drop in the encoding so that it can flip if it needs to. Okay. We don't actually need to pass that because it's actually just already in there. Yeah, I think I'm gonna just pass these in everywhere because they're only going to be available during the header. If I do a translate, for instance, for section headers, that won't be there anymore. And so I want the pattern to be that these have this parameter. For now, we'll say we flip the order if the source encoding is to MSB. Okay. probably want to fix these names. I actually don't like them. So let's go. Type is good. Machine is good. Version is good. Entries off. PH off means segment table off. F off. Not done. Shoff means section table F off. EH size, what is that? I forget. Elf header, EH size. Member holds the elf header size. Okay. Fent size means segment size. Fnum means segment count. Shent size means section size. Schnum means section count. Fent size, segment size, Fnum, segment count, Shent size, section size, Schnum, section count, and then Schusternix is actually the string section index. Schusternix is the string section index. Let's just do it like this. Okay, if it's not being flipped, then we would do, there's our little guy, there's our big guy, But if it is being flipped, we would switch the order on those. Okay, that's close, but it's not good enough. I gotta also cast these to U64s now. Okay, let's just simplify back down to that one term first. Okay, so there's one term. There's two terms. And now I'll set it up so I can go like this and go What's going on here? Why are we off? Oh, you still needed a extra parenthesis. That means you probably did too. There we go. I'm not sure what you mean. How are you making these functions comp time? I'm not. This isn't Zig, so there's no Zig style comp time if that's what you mean. They're compile time. Oh, if you're talking about these are compile time symbols. Like, they get linked at compile time. The compiler just compiles it, inlines it however much it wants, etc. In other words, this is marked as static. It doesn't have to go through the linker. There's no link time linking. Hello. Well, thank you. That's a nice compliment. Yeah, those are basically just telling this is just my way of marking these functions as being things that should link before they go to the linker. They're static functions. I'm sure there are people who have developed a better style for decoding byte swaps than what I've got here. All right. We don't need any of these. Yeah, the ELF file technically comes with a byte at the beginning. There are 16 bytes that each byte is its own thing. Like the order of bytes is defined by the format, not by the target endianness. So each byte, there are 4 bytes for the magic code that always come in the same order no matter what the endianness is, and there's a byte that tells you what data encoding to use, little endian or big endian, basically. And so then you are set up to, if you are, if it's big endian, you just decode it, since we're assuming a little endian target right now. That actually raises a question for me. Do I have in my base layer... I have architecture notes. I could mark. So I have arch x86, 64, arch address size 32 or 64, right? So I could put in like this, right? So that if I ever did have a little big endian target, then what it would happen is flip order would mean we flip the order if the source encoding is big endian and I am little endian, or if I am not little endian and this is not big endian, right? It'd be like this. It's kind of confusing. It'd be like this. Source is big endian. Source big endian does not equal arch big endian. There you go. Now we're supporting big endian targets as well. And yeah, this will generally match. So if I'm parsing x86 files, which I will be, then it'll just always work. But now I've written it in a way here where it should always work for all time. At least for as long as these are the 2 endian types, the 2 data encodings that we care about, right? Um, But yeah, that should give us our headers. And now we have parsed out the raw version of the header and we've normalized the header. So if we compare this to how I did it in PE dump, after parse, there should be a block called dump. Yes. If not good, then unsuccessful parse. If it is good, then let's start with the elf header. Okay, well, let's start from the beginning. The class data and OS ABI are the ones I want to make a special case for. So if, let's see, switch on I, default, we do this. Case elf identification index, class, data, and OS ABI are the interesting ones. M4 printf is not my own implementation, but it's my own customization. The implementation is based on stb printf. So if you find stb underscore s printf right here, this is the header I based it on. So most of the implementation is just copy paste of this, but then I put in like my own capital S format and a couple other custom formats. So I took that as a starting point and customized it for my code base. So I don't directly rely on the real version. Like I don't directly rely on the library. I cloned the library and blended it into my code base, if that makes sense. But I can't claim it as my implementation because it's definitely not. Okay. Now I need to go and set us up. This is the last big thing for today. We've gotten the format stuff started. We've gotten the dumper started. What we haven't done is gotten any sample programs that we can actually run any of this on. Elf dump. Let's go into elf test, and we'll have a program called test there. Okay, so to set that up, I need to go into my build program and set up elf test. Yes. Now we need to get an elf program. Ubuntu. No. All right, let me think. How do I want to do this? I need to set up. There we go. And then let's go into that folder. Set up a little test.c. Just make it simple for now. And I should be able to go clang test.c. Boom. What do I get? A.out. I'm going to rename A.out to test. Is it copy that I'm thinking of? MV, okay. Okay. So if I go to scratch test, this can come live over here in our elf test folder now as our first example. Segmentation fault, elf dump, elf test, test. All right, let's figure out why that would be. Bin dash, thank you. We're gonna actually start a new session today. We're gonna run our debugger on elf dump.exe, and we're gonna give it the argument elf test. What is it called? Elf test slash test. This will be our elf dump debug folder. Begin. Looks good. Looks good. Input data is big enough. We test it. Elf magic is 1. Elf class. Elf encoding. Elf version. Elf extension. We're still good. We grab header 64 raw. Good. And then we say, hey, can we encode that into that? It says, do not flip the order, so the destination just gets a copy of the source. Very good. Okay, so you just print, which we didn't see before, but you're doing the right thing. Oh, those are garbage. How is that happening? Oh, I see what's happening. There we go. Okay. 6, 7, 8, 9, 10. Okay, we are close to have everything the way I want it. There's the identifiers. Okay, now we want to do the elf type. Okay, one of these X lists is, okay, it's the machine type X list, which I did not audit carefully, contains aliases. Duplicate. Duplicate, okay. One, two, three, four, five, six, seven, eight, nine, 10. There we go. All right, getting there, getting there. I'm gonna try to wrap up with the header today. So, just give me a fork order. That'll be easier. Let's do version. That'll be easy enough. Entry. There we go. I mean, that all looks exactly reasonable. The machine type is correct. The version says 1 like it should be. The encoding is little endian, 64-bit. It passed the elf magic test. The header size seems reasonable. These sizes seem reasonable. These counts seem reasonable. That fits inside that. Like, all of that looks right. So we're not done by a long shot with elf dumping, but we got the elf header going, and that included getting all of the elf types ready, getting the dumper sort of program set up, and also getting our first test sample. So that's good progress on this project. We'll definitely keep this up on Wednesday. I'll be back to do more elf dumping. We'll probably get into the sections and the segments, and we'll be able to get most of the elf file dumping within a couple of sessions here. And then we'll go on to doing the generator like we did before. Probably need to think about how to generate some test cases and stuff for elf object files. Things like that still to do. As always, a reminder that this research project, the elf dumper, the PE dumper I did before that, the generator, the visualizer, all of that is a part of the Mr. Fourth Lab project, which I've been working on to research practical problems, bring that information to you, and if you would like to keep me funded so that I can keep doing stuff like this, and you can pitch in on a monthly basis or a yearly basis, go over to mrforth.com/membership and become a part of this project of mine by becoming a supporter or a member and checking out the cool perks that you can get for joining up like that. To all the people who've already done that, it's much appreciated. And with that, I will be signing off for today. Thanks for checking out what I'm doing, and I'll see y'all around the internet. Bye-bye.